Okay, we're in our final Domain 2 Asset Security section, determining the data security controls. All right. Data at rest. By definition, what is data at rest? It is information that is being housed physically, typically in some sort of digital form in storage media, right? It could be cloud storage, it could be file hosting services, it could be data in a database or a data warehouse, it could be literally data in a spreadsheet, data archives, backups, data sitting on a mobile device, all kinds of definitions of data at rest. The data at rest includes both structured and unstructured data. Structured data would be like data that's stored in a database, for example. The type of data, particularly this type of data, data at rest, is susceptible to a lot of different threats from malicious actors to gain access to the information, either for physical theft or for destruction of that data. So to prevent the data from being accessed or modified or stolen, we put into place different protection mechanisms. They could be encryption, it could be password protection, or it could be a combination of both. Depending on what it is, it's broadly defined as what we call DARP. It's not on the slide here, but data at rest protection. You might see that term on the exam. All right. Ultimately, there are three states of data, right? We're talking about one, which is data at rest, but we also define data in motion. That's data that might be traversing a network or residing in a computer memory, to be read or uploaded or processed for execution or whatever. Certainly we have data at rest. That's typically going to be data that's defined as inactive data that's stored physically in a database or a spreadsheet or an archive or whatever. And then we have data in use. That is data that is actively being utilized or being accessed. It could be data in a database or a data warehouse or a spreadsheet, but it's being modified in real time, right? And we have different security considerations for each of these states of data, right? The protection of stored data is a key requirement to an organization. We need to make sure that we maintain the confidentiality, integrity, and availability of that data. Backup tapes, offsite storage, password files, they have to be protected from disclosure or alteration. Alteration is key as well. We need to be able to trust the data that's being stored. The risk is that unauthorized access could jeopardize any of those CIA elements: the confidentiality, the integrity, or the availability of the data. Some different recommendations: encrypt data on removable media to prevent that data from being visible in the case that removable media is stolen. Encryption of data at rest should only include strong encryption methods, AES 256, or RSA or DSA encryption algorithms. This is an asymmetric encryption process. This is a symmetric encryption process. Generally speaking, we do use asymmetric encryption algorithms for data at rest because it is a static static storage of information. We're not trying to encrypt data in motion. Typically, symmetric algorithms are going to be used for encryption or encryption of data in motion. We'll get into that a little bit later on. The encrypted data should remain encrypted when access controls like usernames and passwords fail, meaning that we're going to employ some form of multiple defenses or defense in depth. Data encryption by definition prevents the data visibility. And it's very common to use data encryption to protect data in motion as well as data in rest. The encryption of the data at rest should be certainly strong enough. We're going to talk about this when we get into our cryptography section a little bit later on. But obviously, we're going to include very, very strong encryption mechanisms. Increasing the encryption strength will certainly make the work factor much larger. We'll talk about what work factor is a little bit later on, basically how much effort is required to gain access to the information. Cryptography could be implemented on a database that's housing the data on physical storage. Data encryption keys would probably need to be updated on a regular basis to ensure entropy in the encryption system. So if somebody is trying to discover the crypto variable over time, because we've changed the keys, their efforts are lost because now we have new keys. The encryption keys should always be stored separately from the data, of course. And encryption also provides us the ability to do crypto shredding. Once the data is no longer useful or at the end of its life cycle, crypto shredding provides us the ability to destroy the information, basically deleting the data by deliberately deleting or overwriting the keys, the keying material. Without the keys, we wouldn't be able to recover the data. Make sure that you periodically audit the sensitive data. That should always be part of your policy, and that should happen on a regular basis. And only store the smallest amount of sensitive information that's necessary for you to be able to perform whatever operation it is you're supposed to perform with that particular data. All right? We don't talk about it too much on this slide, but another concept is tokenization. That's an approach for protecting data at rest that allows us to replace essentially sensitive information in that data with non-sensitive substitutes. These are what the tokens are. Tokens themselves have no intrinsic value. They don't really have any exploitable meaning. We don't alter the type or the length of data. We can still process that data as long as we understand the tokenization method that we're using. And tokenization requires a lot less computing resources. It actually allows us to store more information more effectively. All right? I don't know that we're going to get into the concept of tokenization in a whole lot of detail later on. Cryptography can be implemented on the database. Encryption should also enable crypto shredding. We talked about all that. Okay. I mentioned this and I didn't realize that was the next slide. Yes, tokenization is a non-mathematical approach to protecting data at rest, replacing that sensitive data with non-sensitive attributes. Like I said, those are called my tokens. We're not altering the type or length of data. I mentioned all these bullet points. Okay. Lower processing and storage requirements, etc. What are my data at rest recommendations? Have a strategy for not only storing that information, but some sort of data recovery plan if data is lost. Use compliant encryption tools. We'll talk about encryption in the next domain, the advanced encryption standard, which is based on the Rindell algorithm, which we're actually going to go through in detail. I'm going to show you guys specifically how that algorithm works. Not because you need to know it for the test, but because it's nice to know because it gives you an understanding of how encryption works. So we'll talk about all the rounds of encryption, the shift rows process, the mixed columns process, the all of the Boolean operations and so on that are performed in the encryption process. Make sure you use strong passwords, 9+ characters, alphabetic, numeric, punctuation, other characters. I'm going to put a little asterisk here because the concept of strong passwords has kind of been debunked a little bit. Yes, strong passwords are useful. And certainly if the password 9 characters might not be enough in today's world, but I think now 16 characters is kind of the standard. But there is this concept of something called a password haystack. And the challenge with complex, long passwords is that it is counterintuitive to productivity. You have to remember what that password is, or you have to have some way of applying that password when you're authenticating. And ultimately, we all know the story. It ends up being written down or published somewhere, or for ease of access. What would be more prudent when it comes to deploying a password strategy would be to use passphrases. Passphrases can be much larger, but they can also they also provide a larger work factor. We'll get into cryptography and password management later, and I'll show you guys or demonstrate to you this password haystack concept a little bit later on. Use secure password management tools and password sharing methods. Honestly, yes, passwords do play a role still, but what are we using today that really eliminates, a major need for passwords today? We're using multi-factor authentication techniques, tokenized authentication, one-time passwords, TOTP passwords or HOTTP passwords, common access cards, and biometric security, and so on. So passwords are a little bit passé, I guess. Ensure that the covered data that's copied and encrypted, ensure that, let me see what they're trying to say here. Ensure covered data that is copied and encrypted. Not sure what they mean by that. Certainly we understand the encryption piece, right? We want to make sure that the data is encrypted and make sure we destroy old data. Label removable media. That's a really important concept because labels will allow us to determine how that data is going to be handled. And if data is mislabeled, it may be mishandled. All right. I think there was a claim of mislabeling back many years ago when a certain presidential candidate was emailing sensitive information. The labeling wasn't clear, I guess. I won't mention a name. But does it have the appropriate title? Does it identify who the owner is? When was it encrypted? You would try to want to avoid, of course, including information that might be useful to an attacker from a reconnaissance standpoint. Store removable media in a secure locked location. Media storage is a really important concept. Not only in a locked location, but even a remote location. Document the physical location of said removable media. Yeah, we want to know where it is. Absolutely. All right. There are other techniques that we can employ to protect our data. FDE as an example. Disk encryption is a technology that allows us, obviously, to protect information by converting the data on the disk into ciphertext, right? Something that's not readable if somebody gets access to the hard drive. Disk encryption can be done through disk encryption software. It can be built into the hardware like a self-encrypting drive. But every bit of data that goes on that disk should be encrypted. And of course, the whole purpose of that is to prevent unauthorized access to the data. The expression specifically full disk encryption, sometimes referred to as whole disk encryption, means that everything on that disk is encrypted except for the master boot record. That's the bootable component of the disk. That's what starts the operating system and so on. That's typically not going to be encrypted. If it's hardware-based encryption, the master boot record can actually be encrypted and so on. So there are different types of encryption that can be applied, what we call transparent encryption or real-time encryption, or what we call on-the-fly encryption. The transparency factor is we identify it as transparent because basically it just simply means that the data is automatically encrypted or decrypted without any human interaction. The files are accessible immediately with a key that might be stored, and of course the encryption keys are going to be very, very important. Some of the advantages of full disk encryption or self-encrypting drives is a very simple method of deploying encryption because you don't have to do anything. It's automatic, right? It's transparent to the application, to the database, to the user. It typically operates at a hardware-based encryption level and offers high performance. Now, that being said, disk encryption doesn't always replace the need for file encryption in specific situations. So oftentimes we will use file system level encryption in conjunction with disk encryption. And that, again, is just multiple layers of defense that we're going to provide. The reason why we do that is that disk encryption generally uses the same key for encrypting the entire drive, which means that if you get access to that key, then you can decrypt that entire drive as well. Now, some disk encryption solutions do employ the use of multiple keys, maybe a separate key for each volume of the disk and so on. But if the attacker gains access to the computer at runtime, we have access to all the files. Whereas conventional file and folder encryption allows for different keys for different portions of the disk. So we cannot extract information by having a key, for the entire disk. Something that we'll talk about a little bit later on. I don't know if it's in this section or a future section, is something called a TPM. I'm sure you've heard of that before, a Trusted Platform Module. It's basically a crypto processor that's embedded into the motherboard that can be used to do this type of functionality for authentication of the hardware device, and it can also perform encryption functions as well. We'll get into TPMs a little bit later on in more detail. What are some of the limitations of full disk encryption or self-encrypting drives? It addresses a very limited set of threats. It protects only from physical loss of the device. And even in that case, depending on the level of encryption that we've applied, if somebody has physical access to the device, then they're going to be able to eventually, maybe, potentially, discover the crypto variable and be able to get access to that information. It doesn't protect against advanced persistent threats. Advanced persistent threats, we'll get into those a little bit later on, but they kind of classify many different types of attacks. It could be nation states or state-sponsored groups, to gain access to our computer resources over an extended period of time. We'll get into the definition of that later on. We actually have a whole section where we talk about different types of malware, viruses, and so on in a different domain. It doesn't protect against malicious insider attacks, because ultimately that malicious insider might actually have access to the key material, the crypto variable. It maybe only meets minimal compliance requirements. There's no granular access, and we talked about that in that the whole drive is encrypted, etc. Mainstream cloud providers offer functional equivalent FDEs. FDEs make sense for laptops because they are mobile. They're more susceptible to being stolen or lost. FDEs are not typically suitable for most common risks faced in data center environments or cloud environments and so on. So we're going to use other protection mechanisms, to protect those areas, if you will. File level encryption, file-based encryption, or FBE as opposed to FDE, is another type of disk encryption where individual files or directories can be encrypted within the file system itself. We already contrasted this with full disk encryption, where an entire partition of a disk gets encrypted using the same crypto variable. The general purpose file systems that include this file system level encryption would encrypt the files themselves, but do not typically encrypt metadata, the directory structures, the file names, the sizes of the files, modification timestamps, geolocation information. If the metadata needs to be kept confidential, then we may have to use some other encryption technique. All right. The exception to that would be like a ZFS, I think, ZFS file system where metadata is can be encrypted as well. Obviously, we understand generally the difference here. We use software agents installed within the operating system to provide file-level encryption. Those agents intercept all the reads and write calls to disks and apply the policies based on what we've established as our encryption policies. More mature file-level encryption products offer strong policy-based access control to gain access to the file systems, and file access is going to be logged with a event manager integration. What are some of the advantages? Again, it can be transparent to the users. It supports structured and unstructured data. Full disk encryption does that as well. We establish strong controls, assuming we're using, mainstream encryption techniques. But this is the main thing: granular file access and granular file protection. The encryption agents are typically specific to the operating system, so that is a limitation. For many organizations, file-level encryption represents an optimal approach as opposed to full disk encryption. All right. There are different ways of cryptographically securing information at the file level. Of course, the cryptographic keys are going to be very important. Access control to those systems are going to be controlled through something called PKI. We'll talk about that a little bit later on, public key cryptography and public key infrastructure. The individual management of encrypted files can be easier. We can still back up and manage those files independently, and so on. All right. transparent data encryption, or what we call database encryption. The concept of transparent data encryption well, it encrypts information native to a database, right? Obviously, databases are going to house information that's going to be important to our environment, right? We've already talked about data retention techniques and whatnot. Transparent data encryption, is applied to database architectures to encrypt database files. There's variations of this available through Microsoft and IBM and Oracle. This is file level encryption as well. And typically we're focused in this particular case on encrypting data at rest, right? Databases on the hard drive, on backup media, and so on. TDE does not protect data in motion or data in transit or data in use. The TDE is often used for things like compliance or regulatory requirements like PCI DSS. It's part of, TDE is offered as part of SQL databases from IBM. Microsoft SQL Server includes TDE elements, but it was only part of the specific versions of SQL. IBM had it as part of their DB2 database. Oracle included it as part of their advanced security options for their Oracle databases and so on. All right. Again, you don't really need to know the specifics of, vendor specifics. They will never ask you vendor specific information on the exam. So you don't need to know software versions or vendor specific information. Obviously, the advantage is we're protecting against data breaches within the database and protecting against a range of threats against those databases. Limitations: offerings from one database vendor cannot be applied to other database vendors. They each kind of have their own proprietary method. It does not support central administration across multiple databases. Older databases may not support the operation of TDE. We only encrypt the columns or the tables of the database, leaving the system logs, the configuration files open. Database encryption technologies can meet specific technical and tactical requirements. We do not enable organizations to address security across heterogeneous environments or protect data residing outside of the database. As a result, data can leave the organization with leaving significant security gaps. Yeah, because again, it doesn't protect data in motion or data in use. What about application layer encryption? Application layer encryption is a suite of products that expose APIs to streamline adding strong encryption, tokenization, masking, and other cryptographic capabilities to an application. Actually, there's another definition of application layer encryption as well when it comes to data in motion, right? Applying things like transport layer security or secure socket layer functions to data in motion could be considered application layer encryption as well. In this case, they're really literally talking about the programming interfaces within the application itself, adding encryption with within those interfaces. What are the advantages? Developers do not need to develop cryptographic skills, and they use published APIs for the cryptographic functions within the application. That's important because that means that those are tested and reliable functions. We secure targeted subsets of data like sensitive fields in a database. The encryption and decryption occurs at the application layer, so the data is encrypted before it's transmitted and stored. The highest level of security, which provides protection against malicious DBAs or SQL injection attacks. We'll talk about those types of attacks in more detail later on. Tokenization can also significantly reduce things like PCI DSS compliance costs and administrative overhead. That's a specific reference, of course, to the payment card industry, but you know, if the application is more secure, then the data that's being used by the application will be more secure. Some of the limitations: the approaches need to be integrated with the application. That requires development efforts and resources. It may be optimal in cases where security policies or compliance mandates required specific sets of data to be secured. Application layer encryption, including tokenization and format preserving encryption, maintain data formats, avoiding database schema changes, and expect FIPS 140-2 key management to ensure compliance and strong security. FIPS 140-2. That is, we haven't talked about that standard yet, but that is the Federal Information Processing Standard Publication 140-2, and it is specifically the titled "The Security Requirements for Cryptographic Modules." So it defines different levels of security based on FIPS 140. There's actually 4 levels of security. I'm not going to get into it in detail right now. Level 1 being the lowest level of security, level 4 being the highest level of security. But it involves testing and verifying the and validating, if you will, compliance standards based on cryptographic processes. We'll get into that a little bit later as well. Okay. Quick table here. So what we're looking at here is just kind of a table that represents, you know, some of the benefits for data at rest protection. Not something you necessarily need to know for the exam, but I think it's kind of useful to kind of see what, you know, based on the 4 different protection strategies, what's going to provide protection. For example, from particular risks, right? The first risk is data is unrecoverable when the drive is stolen or lost from the data center. All of those mechanisms will be sufficient. The data is made inaccessible to root and system admins, not for full disk encryption, but for the remaining encryption options. Data is made inaccessible to database admins, only applies to TDE and application encryption or tokenization. Data is protected from APTs, advanced persistent threats, using root credentials for data exfiltration. Full disk encryption does not provide protection against that. We create granular access logs for compliance reports and threat analytics. Also, full disk encryption and TDE do not provide that. We assure backups and snapshots are encrypted. Full disk encryption does not provide that. And finally, the last 2, unstructured data, config files, logs, etc. are protected from theft or tampering. TDE does not provide that. Of course, TDE is primarily used for structured data, so that would make sense. Avoid hardware or database vendor lock-in. Full disk encryption and TDE do not provide that because, of course, these are technologies that are specific to particular vendors. All right. For data in transit, by definition, what is data in transit? Data in transit is data in motion, right? And typically we're talking about data that is being sent over the network, but it could be really kind of any type of data in motion. That could be potentially separated into 2 different categories. Information that would flow, for example, over public or untrusted networks like the internet, or data that would flow in the confines of a private network, like a corporate enterprise or your local area network. Data in use is another term that we can use to describe this. Data in use is typically going to be more commonly used in reference to data that might be stored in non-persistent digital memory, like random access memory, CPU caches, or CPU registers. So there is a little bit of a distinction between data in transit and data in use. I don't know that the test really makes that distinction specifically, but you can understand, logically speaking, what that difference might be. What is the description of the risk? Malicious users may intercept or monitor plain text data that's being sent over an unencrypted network using unencrypted protocols like Telnet or FTP or whatnot. A recommendation, make sure that we encrypt that data when it's being transmitted across networks using either secure socket layer or transport layer security. We'll talk about SSL later on, the specifics of SSL and transport layer security. What are the differences between SSL 1 versus SSL version 3, TLS 1.1 or TLS 1.2. For email transmission, we would use public key cryptography for non-repudiation of origin, for confidentiality, as well as message integrity, using tools like Pretty Good Privacy or SMIME, Secure Multipurpose Internet Mail Extensions, for sending and receiving confidential emails, or at least digitally signing emails, or providing non-repudiation of origin. Non-web traffic can be encrypted at the application layer with application level encryption. If an application database is involved, connections could be encrypted using FIPS compliant protocols. FIPS, like I said, is a set of standards for document processing, encryption algorithms, and other IT standards for non-military government agencies and by government contractors and vendors who work with various agencies. We'll probably see a little bit more about that a little bit later on as well. All right, choose an appropriate encryption algorithm. In our next domain, we're going to spend a lot of time talking about cryptography and cryptographic features. I'm really looking forward to that. Longer keys generally mean that we're providing stronger protection. The caveat to that is that it still has to be a good encryption algorithm, right? If there are weaknesses, inherent weaknesses in the algorithm, key space doesn't really matter because we can take advantage of the other weaknesses in that algorithm. So key space is, or the key variable or crypto variable is a significant component to the strength of a cryptographic process, but it's not only the key space that we're going to be concerned with. Make sure you use long or complex passphrases. Kind of contradicts what they had before, 9 characters as opposed to 15 characters. Make sure it contains 2 or 3 character classes, alphanumeric with punctuation. Strong encryption does consume more CPU resources. Unless you're doing hardware-based encryption, where you have specialized hardware specifically designed to perform the encryption. Utilize standards with wireless communications like WPA2 or WPA3, which is what came out after this specific document was published. Also establish appropriate baselines. We know by definition from previous discussions what a baseline is, right? Use a defense in depth approach, meaning that we're not using one single defense mechanism, we're using multiple layers of defense to provide defense for various attacks. If one perimeter or one defense mechanism gets compromised, we have other defense mechanisms that provide us adequate protection for the elements that we're trying to protect. Typically, the first level of defense is going to be some rudimentary enforcement function that would require basic authentication and identification, but then additional layers would maybe provide kind of more sophisticated methods of encryption. Key questions should be considered with your baseline security. Number one, which elements of the enterprise can be protected using that same baseline? Remember, we would like to apply consistent tools across the enterprise. Makes our life a lot easier for management. It also ensures that we have more consistency when it comes to applying security to our enterprise. That's not to say that every tool will apply to many, many different scenarios. And we might have to add compensating controls or other secondary controls in certain cases. But at least let's choose a baseline approach that's going to give us the most amount of protection. Should that same baseline be applied throughout the entire enterprise? Probably, right? I mean, it is a baseline. It's not the meaning, the maximum protection level. It's the baseline. So we can always apply additional protections on a case-by-case basis. What security level should that baseline include? How will those controls forming that baseline be determined? A single baseline reduces implementation costs and ensures same security throughout. That is a interesting concept, actually, when you talk about the same security throughout. The benefit of having this security baseline is that it does make our implementation less complex. But there is a downside to this approach as well. If the baseline is compromised, then the whole system is compromised, right? So there are arguments about having kind of disparate, unique security systems applied throughout the enterprise as opposed to a single solution, and there are pros and cons to both, so just keep that in mind. Baselines ensure a minimal set of safeguards, and the baseline security can be adjusted as your risk changes. Typically, you're going to just simply add more security. You're not going to take away security. So a baseline configuration could still apply. You may just decide to adjust the baseline up to meet specific requirements. Detailed assessment of threats and risk are not necessary. Not for establishing baselines anyway. For establishing additional security controls, you may have to do further analysis. All right. Some examples of baselines. The United States government configuration baseline creates a configuration baseline for IT products and federal agencies. It is what you would expect to see with regard to a kind of a recommendation, if you will, for security principles. The USGCB function provides kind of the same, protection mechanisms that you would expect to see with the implementation of any kind of security concept, right? Identify the assets, identify how we're going to protect those assets, etc. We can get into the configuration baseline if we want to, but I don't think it's necessary to get into the details. It's just another framework that provides guidance for agencies to protect their assets. Information security systems objectives, of course, would always be the CIA triad, right? Apply confidentiality, integrity, and availability. We want to be able to prevent, detect, respond, and recover to security events. A combination of different preventative, detective, response, and recovery measures would be put into place. Preventative means avoiding or deterring a negative event, right? This goes back to when we were discussing risk assessment and risk analysis. Detective, a measure for identifying the occurrence of a negative event. Response, a measure to coordinate responses to contain damage. Containment would be always would always be kind of the initial step, right, to make sure that we are protecting assets that have not been compromised, but also limiting the scope of potential damage, right? Recovery, measure and restore the confidentiality, integrity, and availability that was lost during that negative event. All right, we want to make sure that we're providing protection of the information being processed in transit or in storage. External systems are always assumed to be insecure, no matter what their claim is. That's a very important concept. Even though somebody might claim that a system is secure, we are going to assume that it isn't. We're going to assume the worst case scenario because it's out of our core care of custody, right? We can only guarantee what exists within our environment, all right? Resilience for critical information systems. Critical systems need to withstand major disruption or damage, which of course would be an attack against availability. And as always, with any governance program or framework, there has to be auditability and accountability within that program. Make sure that we have audit trails, that we're generating system logs and alarms, we have notifications and audit actions, and the whole point would be to measure the effectiveness of the program. All right. As far as scoping and tailoring goes, scoping and tailoring would be, of course, applying these baselines and these standards and these guidelines within the scope of the project or within the scope of the systems that we are trying to protect. Scoping guidance identifies the terms and conditions and the applicability and implementation of our security controls to our specific environment. It could be to an individual system. It could be to a range of enterprise systems throughout the enterprise, or it could be to the entire enterprise as a whole. Obviously, as you get more specific, more likely the procedures and the project is going to be more specific, but because it's gonna fit more concisely to that specific tool. But tailoring and scoping gives us the ability to kind of match the characteristics of the system to the characteristics of the protection mechanisms that we're applying. The goal here is to avoid any type of assessment or implementation approach that becomes too costly because it's overwieldy or has too many functions, or it's more complex. We really just want to make sure that we're meeting all of our assessment requirements, and based on our risk assessments and the risk management framework, like 853A or 53B for federal information systems or whatnot, depending on what framework we're applying. We're doing what we're required to do. All right. Oftentimes, more is not necessarily better. More can introduce additional issues or concerns. There is an intrinsic value with scoping and tailoring and supplementation when planning, assessing and assessing the enterprise. All right. All right. Well, that concludes domain number 2. We are now going to move into domain number 3.